Hello everyone. Today we will study graphs in three-dimensional space. Let's look at a simple case first. How do we graph equations with only one variable? How do we graph equations with only one variable? For example, how do we graph this equation s equal to 2? From section 10.1, we know that the graph of s equal to 2 is a plane parallel to the yz plane and passing through 2 in the s-axis. The graph of s equal to 2 is a plane parallel to the yz plane and passing through 2 in the s-axis. It's a plane parallel to the yz plane passing through 2 in the s-axis. How do we graph this plane? Y equal to 3. The graph of y equal to 3 is a plane parallel to the xz plane and passing through 3 in the y-axis. The graph of an equation y equal to 3 is a plane parallel to the xz plane and passing through 3 in the y-axis. That's what we learned in section 10.1. It's a plane parallel to the xz plane and passing through 3 in the y-axis. How's the graph z equal to -1? How's the graph z equal to -1 looks like? The graph of z equal to -1 is a plane parallel to the sy plane. It's a plane parallel to the sy plane and passing through -1 in the z-axis. The graph of z equal to -1 is a plane parallel to sy plane and passing through -1 in the z-axis. Z equal to -1 is here. The graph of z equal to -1 is a plane parallel to the sy plane and passing through -1 in the z-axis. The graph looks like this. It's a plane parallel to xy plane and passing through -1 in the z-axis. That's a graph of z equal to -1. So keep in mind that the graph of equations with only one variable, is a plane parallel to the coordinate planes. The graph of equations with only one variable is a plane parallel to the coordinate planes. The graph of equations with only one variable is a plane. It's always a plane parallel to the coordinate plane. Parallel to a coordinate plane. Coordinate plane means either the xy plane, xz plane, or the yz plane. They are called coordinate planes. Xy plane, xz plane, or yz plane. They are called coordinate planes. Next, let me show you the graphs of equations with two variables. How do we graph an equation with two variables? Let's look at a simple example first. How do we graph this equation, y equal to x cubed minus x in R3? How do we graph this equation, y equal to x cubed minus x in R3? Let's graph this equation in R2 first. How is this graph in R2 looks like? Use your graphing calculator. This graph in R2 looks like this. You can verify this using your graphing calculator. That's a graph of y equal to x cubed minus x in R2. Now, how do we graph this in R3? Let me show you the graph in R3. This equation has only two variables, x and y. That means it doesn't depend on z. When z is 0, we get this graph. When z is 1, we get the same graph. When z is 2, we get the same graph. For every z, we get exactly the same graph. So when z is 0, in the xy plane, we get this graph. So let's graph this curve in the xy plane. That's this graph in the xy plane when z is 0. Now, for example, next, when z is 10, we get exactly the same graph. When z is 10, we get exactly the same graph. When z is 10, we get exactly the same graph. When z is 1, 2, 3, 4, 5, we get exactly the same graph. Connect all these curves together. When z is 1, 2, 3, 4, 5, up to 10, we get exactly the same graph. Connect all these graphs together, we have a surface. When z equal to 1, 2, 3, 4, 5, if we connect all these graphs together, we have a surface. When z is 1, 2, 0, 1, 2, 3, 4, 5, we get exactly the same graph. Connect all these graphs together, we have a surface. This surface is the graph of this equation y equal to sq minus 3 in R3. This surface is the graph of this equation y equal to sq minus x in R3. Next, z equal to 4 minus y squared. How do you graph this equation? This equation has only two variables, y and z. So let's graph the 2D graph first. Let's graph the 2D graph in the YZ plane first. In the YZ plane, assume this is the y-axis. Assume this is the z-axis. The graph in the YZ plane is a parabola. When z is 0, y is positive negative 2. And when y is 0, z is 4. So that's a parabola open downward. That's the graph of this equation in R2. How do we graph this in R3? In this equation, the x component is missing. So that means when s equal to 0, 1, 2, 3, 4, 5, the graph all looks the same. When s equal to 0, 1, 2, 3, 4, 5, the graph all looks the same. When s equal to 0, the graph in the YZ plane is a parabola open downward. That's the graph when s is 0. When s is 1, the graph is the same. When s is 2, the graph is the same. And when s is 4, 5, 6, all graph looks the same, looks exactly the same. To make it easier, let me graph this way. For example, when s is 10, the graph is the same. When s is 1, 2, 3, 4, 5, the graph all looks the same. Then we connect all these curves, connect all these parabolas together. Connect all these parabolas together. Then we can connect all these parabolas together. That's how the graph looks like when we connect all these parabolas together. That's the 3D graph, z equal to 4 minus y squared. That's the 3D graph, z equal to 4 minus y squared. Next example. S squared plus z squared equal to 4. How do we graph this equation? This equation has only two variables, x and z. So let's first of all draw the 2D graph in the xz plane first. Let's draw the 2D graph in the xz plane first. In the xz plane, this is a circle, center and origin with radius 2. In the SC plane, this is a circle, center and origin with radius 2. Now, how do we draw the 3D graph? How do we draw this equation in R3? How do we draw a graph for this equation in R3? How do we draw a graph for this equation in R3? In this equation, we only have xz component. One component is missing. That means when y equal to 0, we have this circle. When y equal to 1, we have the same circle. When y equal to 2, we have the same circle. For LDY, we have exactly the same circle. For LDY, we have exactly the same circle. Connect all the circles, we can get a graph. So, when y equal to 0, when y equal to 0, we have a circle here. That's a circle when y is 0. When y is 1, we get the same circle. When y is 2, we get the same circle. So for LDY, we get exactly the same circle. For LDY, we get exactly the same circle. Connect these circles, we can make cylinder. Connect these circles, we can make cylinder. Connect all these circles, we can make cylinder. So that's the graph of this equation in R3. That's the graph of this equation in R3. Here, in example 1, 2, 3, these three graphs, they are all called cylindrical surface. In an equation, if there's only two variables, its graph in R3 is called a cylindrical surface. Note. The graph of an equation with only two variables in R3 the graph of an equation with only two variables in R3 is called a cylindrical surface. The graph of an equation with only two variables in R3 is called a cylindrical surface. In general, a cylindrical surface is formed by a set of lines passing through a curve in a coordinate plane. Coordinate plane means xy plane, xz plane, or yz plane. They are called coordinate planes, or yz plane. They are called coordinate planes. In general, a cylindrical surface is formed by a set of lines passing through a curve in a coordinate plane and perpendicular to the coordinate plane. So in general, a cylindrical surface is formed by a set of lines passing through a curve in a coordinate plane. For example, this surface is formed by a set of lines passing through a curve in the xy plane and perpendicular to the xy plane. It's formed by a set of lines here. These lines passing through the 2D curve in the xy plane. And they are all perpendicular to the xy plane. This surface is formed by a set of vertical lines, passing through the curve and perpendicular to the coordinate plane. They are formed by a set of lines passing through the curve in the xy plane, in the coordinate plane, and perpendicular to the coordinate plane. So this surface is formed by a set of lines passing through the curve in the coordinate plane and perpendicular to the coordinate plane. It's formed by a set of lines passing through the curve in a coordinate plane. All these lines passing through the curve in the coordinate plane and perpendicular to the coordinate plane. These lines, they are passing through the curve in the coordinate plane and perpendicular to the coordinate plane. So this surface here is formed by a set of lines passing through the curve in the coordinate plane, in the YZ plane. So in the YZ plane, so in the SC plane. Passing through the curve in the SC plane. All these lines passing through the curve in the SC plane and perpendicular to the SC plane. This surface is formed by a set of lines passing through the curve in the coordinate plane and perpendicular to the coordinate plane. All these lines perpendicular to the SC plane. It passing through the curve in the SC plane and all these lines perpendicular to the SC plane. This surface is formed by the lines passing through the curve in the SY plane. And all these lines are perpendicular to the SY plane. This surface is formed by a set of lines passing through the curve in the YZ plane. And every line here is perpendicular to the YZ plane. This surface is formed by a set of lines passing through the curve in the SC plane. And all these lines are perpendicular to the SC plane. Those graphs are called cylindrical surface. If an equation has only two variables, their graphs are called cylindrical surface. Next, let's try to graph equations with three variables. Let's look at a simple case first. Linear equation. How do we graph linear equations with three variables? Remember, for linear equations, s, y, z, they all have degree 1. Every term has degree 1. For example, 2s plus 3y plus 4z equal to 12. This is a linear equation. Every term has degree 1. How do we graph this equation? From last class, we know that equation of a plane has the form of as plus by plus cz equal to d. That's the equation of a plane. And all linear equation has this form. All linear equation with three variables has this form. So we can say that the graph of a linear equation with three variables is always a plane. The graph of a linear equation with three variables is always a plane. In order to fix the plane, we need 3 points. 2 points fix a line. 3 points will fix a plane. Passing through 3 points, we can draw a unique plane. Passing through 2 points, we can draw a unique line. Passing through 3 points, we can draw a unique plane. So in order to graph this plane, we need to find 3 points on the plane. So we need to find 3 points on the plane. In general, try to find s-axis, s-intercept, y-intercept, and z-intercept. So we need 3 points on the plane. In general, we try to find s-intercept, y-intercept, and z-intercept. So for s-intercept, let yz equal to 0. Then 2s equal to 12. S equal to 6. So s-intercept is 6. For the y-intercept, let xz equal to 0. Then I have 3y equal to 12. Solve for y equal to 4. Y-intercept is 4. For the z-intercept, let s y equal to 0. Let s equal to 0 and y equal to 0. Then we have 4z equal to 12. Solve for z. Z is 3. So the z-intercept is 3. S-intercept is 6. Y-intercept is 4. Z-intercept is 3. Once we know 3 points, we can draw a plane. Once we know 3 points, we can draw a plane. S-intercept is 6. 1, 2, 3, 4, 5, 6. That's S-intercept. Y-intercept is 4. 1, 2, 3, 4. Z-intercept is 3. 1, 2, 3. Then 3 point fix the plane. Three-point fix the plane. That's the graph of a plane passing through the points. Passing through 6 in the x-axis, 4 in the y-axis, and 3 in the z-axis. That's the graph of a plane. If we draw a full plane, it looks like this. If we try to draw a full plane, it looks like this. That's the graph of the full plane. A touch. S-axis at 6, y-axis at 4, z-axis at 3. That's the full plane. Next, let me show you how to graph quadratic equations with 3 variables. First of all, let me review quadratic equations in R2. Let me first of all review quadratic equations in R2. How is a quadratic equation in R2 looks like? In R2, usually there are three types of quadratic equations. Equation in the form of y equal to ax squared or s equal to y squared, s equal to ay squared. They are called parabola. It looks like this. A parabola may open upward. It may open upward. It may open downward. It may open to the left, and it may open to the right. They are called parabola. A parabola may open upward. It may open downward. It may open to the left. It may open to the right. Equation in the form of y equal to ax squared or s equal to ay squared. They are called parabola. Equation in the form of ax squared plus by squared equal to c. This is called ellipse. Ellipse looks like this. It may be wider in the x-axis, narrower in the y-axis. Or it may be wider in the y-axis and narrower in the x-axis. Ellipse may be wider in the x-axis, narrower in the y-axis, or it may be wider in the y-axis and narrower in the x-axis. Those are called ellipse. Equation in the form of ax squared minus by squared equal to c, or ay squared minus bx squared equal to c. They are called hyperbola. Equation in the form of ax squared minus by squared equal to c, or ay squared minus bx squared equal to c. They are called hyperbola. Assume a and b are positive. Assume a, b, c are positive. Equation in this form are called hyperbola. The equation in the form of ax squared minus by squared equal to c, the graph looks like this. And the equation in the form of ay squared minus bx squared equal to c. Assuming a, b, c are positive, the graph looks like this. Those are the graph of quadratic equations in R2. Those are graph of quadratic equations in R2. Next, let me show you how to graph quadratic equations with three variables in R3. Those graphs are called quadratic surfaces. Those graphs are called quadratic surfaces. Let me show you a simple example first. Let's the simplest case. 4x squared plus 9y squared. Look at this equation. 4x squared plus 9y squared plus 16z squared equal to 144. Now in this equation, when all coefficients are positive, when we have x squared, y squared, z squared, and all coefficients are positive, we can try to look at the cross section in the coordinate planes first. In the cross section in the xy plane, xz plane, and yz plane. For the cross sections in the xy plane, set z equal to 0. For the cross section in the xy plane, set z equals 0. If I plug in z equals 0, I have 4x squared plus 9y squared equal to 144. This equation represents an ellipse in the SC plane. This equation represents an ellipse in the SC plane. Here, if I set s equal to 0, solve the equation for y equal to positive negative 4. If I set s equal to 0, solve for y equal to positive negative 4. If I set y equal to 0, solve for x equal to positive and negative 6. Then graph the ellipse. It looks like this. That's the cross section in the SY plane. That's the cross section in the SY plane. Now next, for the cross section in the XZ plane, for the cross section in the XZ plane, I set y equal to 0. For the cross section in the XZ plane, I set y equal to 0. If I plug in 0 for y, I have 4x squared plus 16z squared equal to 144. Then this is the equation of an ellipse. This is the equation of ellipse in the SC plane. This is the equation of an ellipse in SC plane. Yeah, if I plug in 0 for x, solve the equation for z equal to positive negative 3. If I plug in 0 for z, solve for x equal to positive negative 6. That's the cross section in the XZ plane. Now, for the cross section in the YZ plane, we set s equal to 0. For the cross section in the YZ plane, set s equal to 0. If I plug in 0 for x, the equation is 9y squared plus 16z squared equal to 144. If I plug in 0 for x, I have 9y squared plus 16z squared equal to 144. This is an ellipse. This is an ellipse in the YZ plane. This is an ellipse in the YZ plane. Then we graph the ellipse here. In the YZ plane. If I plug in 0 for y, solve for z. If I plug in 0 for y, solve the equation for z equal to positive negative 3. If I plug in 0 for z, solve the equation for y equal to positive negative 4. That's the ellipse. That's the ellipse in the YZ plane. That's a cross section, which is the ellipse in the YZ plane. Then let's try to sketch a 3D graph based on these three cross sections. Let's try to draw a 3D graph based on these three cross sections. X, Y, Z. Cross section in the SY plane is an ellipse. S-intercept is positive 6, negative 6. That's a cross section in the SY plane. Next, cross section in the XZ plane. Cross section in the XZ plane. S-intercept is 6. Z-intercept is 3, positive, negative 3. That's the cross section. That's the cross section in the XZ plane. Next, cross section in the YZ plane. Cross section in the YZ plane is an ellipse. As Y-intercept is positive negative 4. Z-intercept is positive negative 3. It looks like this. That's the ellipse. That's the ellipse in the YZ plane. This is the ellipse, the cross section in the YZ plane. That's the cross section in the XZ plane. and that's a cross section in the SY plane. This picture has a name. It's called ellipsoid. This picture has a name. It's called ellipsoid. This picture has a name. It's called ellipsoid. When we have x squared, y squared, z squared equal to some constant, and their coefficients are all positive. When we have x squared, y squared, z squared with equal to a constant, and their coefficients are all positive, this picture is called ellipsoid. And that's the only case we can only look at a cross section and sketch a graph. That's the simplest case. We can sketch a graph based on a cross section. In general, we can do that, but only for this special case. For an ellipsoid, when all coefficients of s, y, z are positive, we can just look at a cross section and draw a 3D graph. Next example, z equal to 4x squared plus 9y squared. How do we graph this equation? Here we can try to plug in different values for z. Let's plug in different values for z and look at the graph in different cross sections. When z equal to 0, what do we get? When z equal to 0, we have 4x squared plus 9y squared equal to 0. If we solve this equation, since 4x squared is greater or equal to 0, 9y squared is also greater than equal to 0. If their sum is 0, they must both be zeros. Since this is greater or equal to 0, this term is also greater or equal to 0. If their sum is 0, that means they must both be 0. So both x and y must be 0. When z is 0, both x and y must be 0. When x and y is 0, we have point 0, 0. So both x is 0, y is 0. Both x is 0, y is 0. So when z is 0, we have a point in the xy plane. When z is 0, the graph is a point. When z is 0, the graph is a point at 0, 0. That's the graph when z is 0. Now, when z is 1, we have 4x squared plus 9y squared equal to 1. That's an ellipse. This is an ellipse. This graph is an ellipse. If I set x equal to 0, y equal to plus or minus 1/3. This is an ellipse. If I set x equal to 0, y equal to plus minus 1/3. If I set y equal to 0, s is plus minus half. If I set y equal to 0, s is plus minus half. So in this ellipse, intersection in x-axis is positive negative half. So it's wider in the x-axis. Intersection in the y-axis is plus minus 1/3. It's narrower in the y-axis. This ellipse is wider in the x-axis, narrower in the y-axis. It's wider in the x-axis, and it's narrower in the y-axis. So that's the graph when z equal to 1. When z equal to 2, we have 4x squared plus 9y squared equal to 2. If I let s equal to 0, solve the equation for y. Y is plus minus radical 2 over 3. If I let y equal to 0, s is plus minus radical 2 over 2. So this graph is also ellipse, and it's wider in the x-axis and narrower in the y-axis. It's a larger ellipse, but it's also wider in the x-axis, narrower in the y-axis. That's a graph when z equal to 2. So we can see that here. As z increases, the ellipse gets larger. As z increases, the ellipse gets larger. Now, as z increases, the ellipse gets larger. Can z be negative here? Can z be negative? Can we plug in negative z values? We know that 4x squared is always greater or equal to 0. 9y squared is also greater or equal to 0. So now sum cannot be negative. Here, in this equation, z cannot be negative. So we don't need to plug in negative value for z. Now let's try to draw a rough graph. We know that when z is 0, the graph is a point. When z is 1, the graph is an ellipse. It's wider in the x direction. Narrower in the y direction. It's wider in the x direction. When z equal to 1, the graph is an ellipse. It's wider in the x direction. Narrower in the y direction. When y is 2, we have a larger ellipse. And as z increases, the ellipse gets larger. Now next, let's look at cross section in the xz plane and yz plane. As z increases, the ellipse gets larger. Next, let's try to look at the cross section in the xz plane and yz plane. Since we are finding level curve for z values, next try to find cross section in the xz plane and yz plane. For the cross section in the xz plane, set y equal to 0. For the cross section in the xz plane, set y equal to 0. If we plug in 0 for y, we have z equal to 4x squared. That's a parabola open upward. That's a parabola open upward. That's the cross section. That's the cross section in the xz plane, which is a parabola open upward. For the cross section in the yz plane, set s equal to 0. For the cross section in the yz plane, set s equal to 0. Z equal to 9y squared. That's a parabola open upward. In the yz plane, it's also a parabola open upward. So the cross section in the yz plane is a parabola open upward. The cross section in the xz plane is also a parabola open upward. This is the z-axis. This is the y-axis. And this is the s-axis. This is a cross section in the YZ plane, and this is a cross section in the XZ plane. This graph is called elliptic paraboloid. Elliptic paraboloid. This graph is called elliptic paraboloid. So, when we're looking for level curves along z-axis, we must find a cross section in the XZ plane and YZ plane. In general, when we're looking for cross section along z-axis, we must find a cross section along the XZ plane and YZ plane. If we're looking for cross section along x-axis, we must looking for cross section in the XY plane and XZ plane. If we're looking for level curve along y-axis, we must looking for cross section on XY plane and YZ plane. If we are looking for level curves along z-axis, we must find cross section in the XZ plane and YZ plane. If we find level curves along x-axis, we need to find cross section along XY plane and XZ plane. If we are looking for cross section along the y-axis, we must find the cross section in the XY plane and YZ plane. So let's a rough 3D graph. This graph is called elliptic paraboloid. Next example, z equal to 4x squared minus 9y squared. So here, since z has power 1, both s and y has power 2, z has power 1. Let's try to find the level curves along the z-axis. Since both s and y has power 2, z has power 1. In this situation, try to find level curves along the z-axis. When both x and y has power 2, z has only power 1, try to find level curves along the z-axis. Similarly, if s has power 1, y and z has power 2, try to find level curves along x-axis. If y has level 1, y has power 1, x and z has power 2, try to find level curves along the y-axis. Here, since z has power 1, both s and y has power 2, try to find level curves along the z-axis. So here z could be positive, it could be positive, it could be negative. Because 4y squared minus 9z squared, it could be positive, it could be negative. So let's test for some positive number first. When z equal to 0, we have 0 equal to 4x squared minus 9y squared, which means 9y squared equal to 4x squared. If I solve an equation for y squared equal to 4 over 9x squared, y equal to plus or minus 2 over 3x. Those are two lines. If we graph it, those are two lines. When x is 3, y is 2. When x is 3, y is 2. When x is 3, y is positive negative 2. When x is negative 3, y is also positive negative 2. So this graph is 2 lines. Y equal to positive negative 2/3 of x. The graph is 2 lines. When z equal to 1, we have 4x squared minus 9y squared equal to 1. When z equal to 1, we have 4x squared minus 9y squared equal to 1. This equation represents a hyperbola. This equation, the graph is a hyperbola. This equation, the graph is hyperbola. When s is 0, there's no solution for y. When s is 0, there's no solution for y. When y is 0, s equal to plus minus 1 over 2. When y is 0, s is plus minus 1 over 2. And the graph is hyperbola. It looks like this. When z is 2, we have 4x squared minus 9y squared equal to 2. If I plug in 0 for x, there are no solution for y. But if I plug in 0 for y, s equal to plus minus radical 2 over 2. Since this graph is hyperbola, it touches plus minus radical 2 over 2, somewhere here. So you can see that as z increases, the hyperbola moving away from the origin. As z increases, hyperbola moving away from the origin. Now let's test for some negative z values. When z is negative 1, we have 4x squared minus 9y squared equal to negative 1. This equation can be rewritten as, if I multiply both sides by negative 1, this equation can be rewritten as 9y squared minus 4x squared equal to 1. If I multiply both sides by negative 1, this equation can be rewritten as 9y squared minus 4x squared equal to 1. If I plug in 0 for y, there are no solution for x. But if I plug in 0 for x, solve the equation for y equal to plus minus 1 over 3. If I plug in 0 for x, solve for y equal to plus or minus 1 over 3. When z is negative 2, this equation can be rewritten as 4x squared minus 9y squared equal to negative 2. If I multiply both sides of the equation by negative 1, this equation can be rewritten as 9y squared minus 4x squared equal to 2. That's a hyperbola. This equation represents hyperbola. If I plug in 0 for y, there are no solution for x. If I plug in 0 for x, y equal to plus minus radical 2 over 3. This number is larger than 1/3, so it's further away from the origin. So for negative z, as z decreases, hyperbola moving away from the origin. For negative z, as z decreases, hyperbola moving away from the origin. So this line here is z equal to 0. This line here is z equal to 1. That's the level curve when z equal to 2. This curve here is z equal to negative 1. This curve here is z equal to negative 2. So as z increases, when z is positive, as z increases, it moves away from the origin. When z is negative, as z decreases, it moves away from the origin. Now let me draw a loft graph first. For hyperbola, it's not easy to graph it. Let me draw the hyperbola in a cube. It will be a little easier. It's not easy to graph hyperbola. Let me draw hyperbola in a cube. Now, suppose this plane is z equal to 2. Suppose this plane is z equal to negative 2. When z equal to positive 2, it's hyperbola open in the direction of s-axis. It's hyperbola open in the direction of s-axis. That's the hyperbola when z is 2. Now, when z is negative 2, the graph is hyperbola open in the y direction. Next, we can remove those unnecessary lines. What's left is 2 hyperbolas. Next, let's look at the cross section. Since we are looking for level curve along z-axis, Let's find a cross section in XZ plane and a YZ plane. For cross section in the XZ plane. For cross section in the XZ plane, I let y equal to 0. If I plug in 0 for y, the graph is z equal to 4s squared. If I plug in 0 for y, the graph is z equal to 4s squared. Let's a parabola open upward. So in the XZ plane, we have a parabola open upward. In the SZ plane, we have a parabola open upward. For the cross section in the YZ plane, let s equal to 0. If I plug in 0 for x, I get z equal to negative 9y squared. Z equal to negative 9y squared. That's a parabola open downward. So in the YZ plane, we have a parabola open downward. In the YZ plane, we have a parabola open downward. Now let's try to draw the parabola here. In the XZ plane, we have a parabola open upward. In the SZ plane, we have a parabola open upward. In the YZ plane, we have a parabola open downward. In the YZ plane, we have a parabola open downward. That's a parabola in the XZ plane. And that's a parabola in the YZ plane. This is the z-axis. This is the y-axis. This is the x-axis. That's the origin. This graph is called hyperboloid paraboloid. Hyperboloid paraboloid. Hyperboloid paraboloid. It's called hyperbolic paraboloid. This graph is called hyperbolic paraboloid. So keep one thing in mind. When x and y both have squares and z has only power 1, we are looking for level curves along the z-axis. And when we're looking for level curves along z-axis, we need to find cross-section in xz plane and yz plane at the end. When x and y both has squares and z has power 1, looking for cross-section along the z-axis. But when x has power 1, y and z has power 2. Here we're looking for cross-section along the z-axis. We have y equal to x squared minus z squared. When s and z has power 2, y has power 1, we're looking for cross-section along the y-axis. Next example, s squared plus 4y squared minus 4z squared equal to 0. In this equation, s squared and y squared, they both have positive coefficient, but z has negative coefficient. So try to move z over, and then find the level curves along the z-axis. Move z over, find the level curves along the z-axis. So let's plug in different values for z, find the level curves along the z-axis. When z is 0, what do we get? When z is 0, we have s squared plus 4y squared equal to 0. Since s squared is greater or equal to 0, y squared is greater or equal to 0. If they are both greater or equal to 0 and their sum is 0, then both x and y must be 0. Both s and y must be 0. If both s and y is 0, we have 0, 0. When z is 0, we have point s equal to 0, y equal to 0. When z is 0, we have a point s equal to 0, y equal to 0. That's the point when z is 0. Now, when z is 1, we have s squared plus 4y squared equal to 4. But since we are taking square for z, that means when z equal to plus or minus 1, the graph is the same. That means when z equal to plus or minus 1 squared, we get 4. So that means when z equal to plus or minus 1, we get the same level curves. When z is plus or minus 1, we get exactly the same curve. This is an ellipse. This is an ellipse. This equation represents an ellipse. When s is 0, y is plus or minus 1. When y is 0, s is plus or minus 2. When s is 0, y is plus minus 1. When y is 0, s is plus minus 2. It's wider in the x-axis, narrower in the y-axis. It's an ellipse. It's wider in the x-axis, narrower in the y-axis. When z is plus or minus 2, I have s squared plus 4y squared. If I plug in 2, 2 squared is 4, 4 times 4 is 16. Here, when s is 0, that's an ellipse. When s is 0, I have y equal to plus or minus 2. When y is 0, I have s equal to plus or minus 4. That's the ellipse, but it's wider. This is ellipse, but it's wider. It's larger. It's wider in the x-axis, narrower in the y-axis. So here we can see that as z increases, the ellipse gets larger. As z increases, the ellipse gets larger. Now, based on a level curve, let's draw a loft graph first. When z is 0, the graph is a point. When z equal to plus or minus 1, we have an ellipse. The graph is an ellipse. When z equal to plus minus 2, the graph is a larger ellipse. That's a loft graph based on the level curves. Next, let's try to find a cross section. Since we are looking for level curves along the z-axis, let's find a cross section in the xz plane and yz plane. For the cross section in the xz plane, let y equal to 0. If I let y equal to 0, I have s squared minus 4z squared. If I let y equal to 0, I have s squared minus 4z squared. This equation can be rewritten as 4z squared equal to s squared. Z squared equal to half of x squared, a quarter of s squared. Z squared equal to 1 over 4 s squared. So z equal to plus or minus half s squared, plus or minus half x, which are two straight lines. In the xz plane. We have two straight lines in the xz plane. For the cross section in the yz plane, set s equal to 0. If I plug in 0 for x, I have 4y squared minus 4z squared. Equal to 0. This equation can be rewritten as 4z squared equal to 4y squared. So z squared equal to y squared. Z equal to plus or minus y. This graph is also two straight lines in the yz plane. This graph is also two straight lines in the yz plane. So for the cross section in the yz plane, we have two straight lines. For the cross section in the yz plane, we have two straight lines. For the cross section in the xz plane, the graph is also straight line. It's also two straight lines. That's the cross section in the xz plane. This is the z-axis. This is the y-axis. And this is the s-axis. This graph is called elliptic cone. This graph is called elliptic cone. Next example, x squared plus 4y squared minus 4z squared equal to 16. Every term has a square. Every term is quadratic, but x and y has positive coefficient. Z has negative coefficient, so move Z over. Move Z over. Find level curves along the z-axis. Since Z has negative coefficient, move Z over. Find level curves along the z-axis. So if I move Z over, I have x squared plus 4y squared equal to 16 plus 4z squared. Find level curves along the z-axis. When z equal to 0, we have x squared plus 4y squared equal to 16. This is an ellipse. This equation represents ellipse. When s is 0, y equal to plus minus 2. When y is 0, s is plus or minus 4. It's wider along x-axis, narrower along the y-axis. It's an ellipse. Wider along x-axis, narrower along the y-axis. That's the curve when z is 0. When z is plus or minus 1, since we have z squared here, when I plug in plus or minus 1, we get exactly the same equation. Since we have a z squared here, when I plug in plus or minus 1, we get exactly the same equation. So when z is plus or minus 1, we have x squared plus 4y squared equal to 20. When s is 0, y equal to plus or minus radical 5. When y is 0, s equal to plus or minus 2 radical 5. So we get a wider ellipse. We get a wider ellipse. When z is plus or minus 2, when z is plus or minus 2, we have s squared plus 4y squared equal to 16 plus 16 is 32. That's an ellipse. This equation also represents ellipse. When s is 0, we have 4y squared equal to 32. Y equal to plus or minus y equal to plus or minus 2 radical 2. When y is 0, s equal to plus or minus 4 radical 2. We get even wider ellipse. So we can see that as z increases, the ellipse gets wider and wider. As z increases, the ellipse gets wider and wider. So let's draw a Loft graph based on the level curves first. When z is 0, we have an ellipse. When z is plus or minus 1, we have a wider ellipse. When z is plus or minus 2, we have an even larger ellipse. So that's a loft graph based on the level curves. That's a loft graph based on level curves. Next, let's look at the cross section on the XZ plane and the YZ plane. For a cross section in the XZ plane, let y be 0. If I plug in 0 for y, I have x squared minus 4z squared equals 16. If I plug in 0 for y, I have x squared minus 4z squared equals 16. This is a hyperbola. This is hyperbola. It's a hyperbola in the XZ plane. This is a hyperbola in the XZ plane. When I plug in 0, there's no solution for z. But when I plug in 0 for x, there's no solution for z. When I plug in 0 for z, x is plus or minus 4. So the hyperbola open like this. That's a hyperbola in the XZ plane. For the cross section in the YZ plane, I let x equal 0. If I plug in 0 for x, I have 4y squared minus 4z squared equals 16. That's a hyperbola. That's a hyperbola in the YZ plane. When I plug in 0 for y, there's no solution for z. But when I plug in 0 for z, y is plus or minus 2. So the graph is hyperbola. It touches y-axis at plus or minus 2. That's how the graph looks like. Then draw the cross section together. The cross section in the SY plane, in the YZ plane, is a hyperbola. The cross section in the YZ plane is hyperbola. The cross section in the SY plane, so the cross section in the SC plane is also hyperbola. Z-axis is here. This is the y-axis. This is the x-axis. This graph is called hyperboloid. It has only one sheet. This is called hyperboloid. And this graph, this hyperboloid has only one sheet. This graph is called hyperboloid. This graph has only one sheet. Some hyperboloid may have two sheets. Some hyperboloid may have two sheets. Let me show you next example. Some hyperbole may have two sheets. Next example, g squared minus 4x squared minus y squared equal to 4. In this equation, s, y, z, they all have square, but x and y has negative coefficient. X and y has negative coefficient. Z has positive coefficient. That's different. S and y, they both have negative coefficient, but z has positive coefficient. So move z over, and find narrow curves along the z-axis. Move z over. We have 4x squared minus y squared equal to negative z squared plus 4. Then multiply both sides by negative 1. I get 4x squared plus y squared equal to z squared minus 4. Find narrow curves along z-axis. When z equal to 0, I have s squared, 4s squared plus y squared equal to negative 4. This equation has no solution. Because perfect squares, the sum of perfect squares is positive. It cannot be negative 4. So in this equation, there are no solutions. That means no graph when z is 0. There are no graphs when z is 0. No surface when z is 0. When z is plus or minus 1, since we have z squared here, I can plug in plus or minus 1 for z. The equation is the same. When z is plus or minus 1, I have 4s squared plus y squared equal to negative 3. The sum of perfect square cannot be negative, so there are no solutions. Which means there's no graph when z equal to negative, when z equal to plus or minus negative, when z equal to plus or minus 1, there's no graph. When z equal to plus or minus 2, I have 4s squared plus y squared equal to 0. 2 squared is 4, 4 minus 4 is 0. So if the sum of perfect square is 0, they must both be 0. If the sum of perfect square is 0, they must both be 0. So s is 0, y is 0, with a point 0, 0. When z is plus or minus 2, we have point 0, 0. When z is plus or minus 3, we have 4s squared plus y squared equal to 3 squared is 9, 9 minus 4 is 5. This equation is an ellipse. This equation represents an ellipse. When s is 0, y equal to plus or minus radical 5. When y is 0, s equal to plus or minus radical 5 over 2. So it's wider in the y-axis. It's wider along the y-axis, but narrower around the s-axis. This ellipse is wider along the y-axis, but narrower along the x-axis. When z equal to plus or minus 4, 4 squared is 16, 16 minus 4 is 12. We have 4s squared plus y squared equal to 12. This equation represents ellipse. When s is 0, I have y squared equal to plus or minus 2 square root of 3. When y is 0, s equal to plus or minus radical 3. So this ellipse is wider along the y-axis, narrower along the s-axis. So here we can see that as z increases, the ellipse gets larger. As z increases, the ellipse gets larger. Now next, let's draw a loft graph based on the level curves. Let's draw a loft graph based on the level curves. When z is 0, there are no graphs. When z is 1 and -1, there are no graphs. When z is 2 and -2, when z is 2 and -2, we have 1 point. We have 1 point for each. When z is plus or minus 3, we have an ellipse. When z is plus or minus 4, we have an even larger ellipse. When z is plus minus 4, we have even larger ellipse. Next, let's look at a cross section in the xz plane and yz plane. Let's look at a cross section in the xz plane and yz plane. For cross section in the xz plane, let y equal to 0. If I plug in 0 equal to y, I have z squared minus 4x squared equal to 4. This is a hyperbola. This is hyperbola. If I plug in 0 for z, there are no solution for x. But if I plug in 0 for x, z is plus or minus 2. For cross section in the yz plane, we set s equal to 0. If I plug in 0 for x, I have z squared minus y squared equal to 4. That's a hyperbola. This graph is a hyperbola. It's a hyperbola in the yz plane. When I plug in 0 for z, there are no solution for y. But when I plug in 0 for y, z is plus or minus 4. So z is plus or minus 2. That's a hyperbola. So the cross section in the yz plane is a hyperbola. The cross section in the yz plane is a hyperbola. Hyperbola has two pieces. One piece here, another piece here. And the cross section in the xz plane. Cross section in the xz plane is also hyperbola. That's the z-axis. That's the y-axis. That's the x-axis. This graph is also called hyperboloid. This graph is also called hyperboloid. And this graph has two sheets. This graph is also called hyperboloid. And it has two sheets. This graph is also called hyperboloid, and it has two sheets. In a textbook, on page 584, table number 1, there are all 6 quadric surfaces. Memorize them all. In the textbook, in page 584, table number 1, there are all 6 quadric surfaces there. Memorize them all.